And Andrzej is a professor at the University of Arizona, and he works on external graph theory as well as distributed computing and the connection between the two. And he has quite a few interesting results on matching and domination in sparse graphs. And today his talk will be about matching in sparse graphs. And please go ahead, Andrzej.
Okay, thank you very much for the introduction, and I would like to thank organizers for inviting me. And indeed, in this talk, I will talk about matchings, so distributed algorithms for matchings, and then about some generalizations of matchings. Now, bad news is that I've got too many slides, but good news is that I will skip every second one of them, so it shouldn't take that long. Okay, so let me start with the definition of a matching. So a matching is just a set of edges such that these edges are independent. So these edges do not share a vertex. And in this talk, I will mention two types of special matchings. One of them is called maximal, and then the second one is called maximum. So a maximal matching in a graph G will be a set of edges such that it's not possible to find a matching M star such that this M star contains this M as a proper subset. Okay, so you simply cannot extend it. And then the maximum matching on the other, or a maximum matching on the other hand, will be a matching M such that the size of it is the largest possible. That's the notation that I will use. So if you see it on some of the slides, then this will be referring to this quantity, namely the size of a maximum matching. Now, of course, there's a connection between these two, namely in view of the theorem of Berge, we know that a maximal matching is an approximation of a maximum matching, namely its size will be at least 1/2 of the size of the maximum. And I will be using, or at least mentioning, the generalization of this observation later on. Now, just a warning, although this maximal matching is going to show up throughout the talk, I'm going to mainly focus on the maximum, and specifically, I will be interested in approximating this maximum, this quantity, which is the size of a maximum matching. So this will be the main goal of this talk. Okay, so although everybody knows that, let me just mention very briefly that I will focus entirely on the local model. I'm not going to pay too much attention to congest and to sort of details which are coming from the model. The main objective of the talk will be to sort of illustrate some of the ideas. Also, I will be assuming, although this is not going to show prominently throughout the talk, I will be assuming that each vertex is an identifier. Again, I'm not going to pay too much attention to these identifiers, but definitely there's an assumption that they are coming from some set of size, which is polynomial in the order of a graph. Let's just assume that it is in N, where N is the order of a graph. Okay, so before continuing to the special classes of graphs that I will be interested in this talk, let me sort of mention a few results. This is not intended to be comprehensive, it's just a few results which I think are relevant to what I'm going to talk about in general graphs. Okay, so I would like to mention, I mean, there's a big history of studying, especially the maximal matching problem, and there are many, many results on distributed algorithms in local and congest and so on models for this problem. One recent result that I would like to mention is this one by Fisher, which gives a deterministic log cube n time algorithm that finds a maximal matching in any graph G. So the fact that the complexity is polylogarithmic in the order of the graph, this was known for quite some time, but I guess the best bound before that one was log to the fourth of log n to the fourth power. by Hanczkowiak-Karski and Pagonesi, and it was done more than 10 years ago. So this is quite a nice improvement which was recently obtained. Okay, so another result that I would like to mention for general graphs is this one by Ghaffari, Kuhn, and Harris. And this one gives basically log to the 7th power of n over epsilon to the 9th algorithm, which finds a 1 minus epsilon approximation of the maximum matching in general graphs. Again, it was known for quite some time that there are algorithms which find these 1 minus epsilon approximations in polylogarithmic number of time, but typically this complexity was significantly, and I do mean significantly, larger. Okay, so let me move on and talk about classes of graphs that I will be interested in this talk. So basically, I will be interested in two classes. I will be interested in graphs that do not contain a complete graph on m vertices as a minor. M here will always be a fixed integer, and the algorithms will know what this quantity is. And so this class will sort of feature in the second part of the talk. And the second class of the graphs that I'm going to mention will be these graphs of bounded degeneracy or bounded arboricity, as was mentioned before. These two are equivalent if you don't pay attention to the constants, and I'm not going to. So this will be the second class that I'm going to discuss in this talk. Okay, so let me move on and let me sort of mention the first result that I have here. And this one will be on approximating a maximum matching in graphs which have bounded arboricity. So it turns out that this is not difficult to do. It's possible in big O of log star n rounds, find a matching M such that the size of this matching is at least 1 minus epsilon, the size of the maximum matching. So this sort of settles the case of approximating a maximum matching. Well, I'm making here a small leap, but let's just say that it settles the case in view of Lineal's lower bound of log star n for a maximal and then generalizations of it. This settles the case of graphs of bounded arboricity. Okay, so let me sort of try to give a very brief idea of how this algorithm proceeds, which is again quite basic, and sort of a few words about the analysis which is involved in this work. So not surprisingly, what we want to consider in the argument here and in the algorithm is a set of vertices that have a bounded degree. By the way, because of that, I am assuming that arboricity is bounded by a constant. Okay, the algorithm, the theorem is meaningless if it is something which depends on n. So I'm looking at the set of vertices of degree bounded by some constant c, not going to specify it. This depends on a and epsilon, and I'm going to do something to this set. But it turns out that it's just not enough to discard the remaining vertices. You've got to sort of keep track of them as well. So there will be two additional sets of vertices which are going to show up. So U1, this is the vast majority of the graph. This set contains vertices of degree bounded by some constant c. U2, this will be sort of vertices outside of U1 that do have a big degree to U1. Okay, again, not going to specify C1. C1 is slightly larger than C, and yeah, you've got to be careful about these constants to make this thing work. And then the third set that I have here is U3. So these are the remaining vertices. Okay, so how do they come to play? So they come to play in the following fashion. So we've got U1, we've got then U2, which we have to be careful with, and then U3. turns out that U3 can be neglected. So it's safe to discard these vertices because they have a big degree, but this degree is not 2U1. It's definitely not 2U3, at least not on average, because the graph has a bounded hypericity. So it must be 2U2. So they have a decent degree 2U2. At the same time, so you will be able to bound the size of U3 by the size of U2 if you set these constants carefully enough. At the same time, U2, these guys, they do have a big degree to U1, and vertices of U1 have degree which is bounded by a constant. So by appealing to Hall's theorem, you can argue that there will be a matching in this, sorry for the mess, in this here bipartite graph, which will saturate all of the vertices from U2. So if you can bound anything with respect to U2, then you can also bound it with respect to the size of the maximum matching. And that's the idea. Now with U2, you have to be careful, and here and the three sets that we've got to here pay attention to. So one of them is L22, and these are basically vertices that have a decent degree or big degree, let's say, inside U2. Then there's this set L21, and these guys, on the other hand, they do have a decent degree or a big degree to U1. And then there will be the remaining vertices. Okay, so now here's how the algorithm proceeds. You observe that this set, so U1 plus everything in U2, which is outside L of 2.1 and L22, this one has a bounded degree. Maybe not by C, but something like 4 times C will do. So if you have a bounded degree, then you can apply this sort of method of Hopcroft and Karp, which involves augmenting paths. And the degree is bounded, so in log star n, you can find an independent set in an auxiliary graph, and then you can augment these paths. And in this fashion, you will be able to find a matching M, which is a good approximation of a maximum matching in just this restriction. Okay, now I already made an observation about U2. Turns out that these vertices can be discarded. It also turns out that these vertices in L22, they can be discarded. The only worry is now the vertices in L21, and they can be important. They absolutely can be critical to the size of a maximum matching. So you've got to carefully play with these. I'm not going to go into detail, this sort of requires some work, but just to give you a feeling of what's going on now with this small set, well, I will have here, after finding this approximation M of the matching in this piece of the graph, I will have 2 types of vertices over here. The vertices that have a big degree to the nodes which are already saturated, and then vertices that have a big degree to the part which is not saturated by M. Now, turns out that if this first set is relatively big, then you already are safe. Namely, this matching M, the one that you found a moment ago, will be enough to be able to discard the vertices in L21. If on the other hand, this is small, then it turns out that you've got to do a little bit more. Now, it's not that the algorithm checks if it is small or not, but the analysis definitely relies on the second case. So in sort of the second case, what comes critical is another matching, which will be a matching, an approximation of an maximum matching in the graph, which is induced by unsaturated vertices and then these vertices of L21. So, I mean, you've got to do some preparation, but basically you find another approximation by appealing to this Hopcroft-Karp technique, and then you combine them. So then the result will be just the union of these 2. Okay, so I already said that indeed the whole analysis relies on Hall's theorem and the observation that there will be a matching which is proportional to U2. This is not difficult. You can use the bound for arboricity and then the fact that there's a matching of that size to claim that these are safe to be discarded. Okay, so these two sets do not pay any attention. And then L21, that's something that must be carefully analyzed. Okay, so this one, the analysis here again relies on the whole sphere. Okay, so that's just a taste of how one can approximate the maximum matching in these graphs of bounded arboricity. Okay, so I will be moving to the second part of the talk in which I will talk about certain generalizations of matchings. And specifically, I will be interested in these two generalizations. One is called F factors or F matchings, and the second one is called B matchings. A warning, you might know, especially this first one, under a slightly different name, because sort of nomenclature is not ubiquitous and not uniformly fixed. Okay, but in this talk, an F matching or an F factor, if you wish, this will be again a set of edges. But maybe before that, a starting point to considering both of these is, of course, a graph G and then some function on the set of vertices. So here I have a function f from the set of vertices to the set of positive integers. So now an F factor will be a set of edges f such that every vertex is incident to at most f of the edges. So critically, it's a set of edges. Okay, so you cannot pick any edge more than once. Again, that's the notation that I will use for the size of the maximum F matching in graph G. And although I'm not going to talk all that much about the B matchings because of the time constraints, let's just say that in this concept, I've got a function B as before on the set of vertices, and then a B matching will be a multiset of edges, such that every vertex is incident to at most B of the edges. Again, that's the notation. I'm not sure if you're going to see it in the rest of the talk or not, but that's in case you do, this is the meaning of it is the size of the maximum B matching. Now, in general, B matchings are not all that interesting in the realm of distributed algorithms, because there's a known reduction by Tutt, which will reduce B matchings to matchings. But the reduction is by blowing up vertices and then using complete bipartite graphs. So the problem with sparse graphs is that if you apply this reduction, it's going to take you outside of the realm of sparse graphs. Okay, so you simply cannot apply it and reduce the problem to the problem of a maximum or approximating a maximum matching. Well, anyway, as I said, I will mainly focus on F matchings. Okay, so in the second part of the talk, I will critically assume that the graph is Km minor 3. Okay, so this will be a subclass of what we had in the previous theorem, but also the problem is much more general. In the case when F is equal to 1, then this reduces to a regular notion of a matching. Okay, and to approach this problem of finding or approximating a maximum F matching in a graph G, which is Km minor 3, I will be proceeding in two major steps. In the first major step, I will be sort of trimming this graph this graph G to come up with a graph H, which accomplishes the following two objectives. First of all, I do not want to lose the value of the maximum F matching. So it will have to be the case that the size of a maximum F matching in H is the same as the size of a maximum matching of G. H will be definitely a subgraph of G. And then in the second, not in the second phase yet, then the second condition will be that the size of a maximum F matching of H should be proportional to the number of vertices in H. Now, once I have that, I will be applying a clustering procedure. That's something which by now is quite well known and has been generalized in a few different ways. And we'll be partitioning V of H, and I will find optimal solutions in each of the partition classes. Going to talk about it in a few minutes in a little bit more detail. And then what will be returned is the union of these locally found solutions. Okay, so these two phases. Now, to keep it well organized, let me start with phase 2 rather than phase 1. Okay, so we've got the following fact. If I have a graph which is km minor 3, then it is possible to find the following partitioning of the vertices of H. So I can partition the vertices into a bunch of clusters so that, first of all, each cluster has a constant diameter. Second, the number of edges between different clusters can be bounded from above by some small constant times the order of H. And then I guess the third condition is that the time is acceptable. So this can be done in big O of log star of H, of the order of H, number of rounds. Not going to go in detail through this algorithm. Basically, the idea is to do a bunch of iteration, and in each iteration to find a collection of sort of useful stars and to contract these stars, and then to iterate with the graph which is obtained by this contraction. Okay, so now once I have that partitioning, let me just sort of finish this idea, although this is now hopefully easy to see what's going to happen. We find an optimal or an approximation of an optimal, if you're not comfortable with finding really an optimal one, an optimal F matching in each of these pieces, which has again a constant diameter, and then we return the union of them. Now the question is why it works, and of course it works because you can say something about the edges which are being discarded, namely the edges between these two different clusters. Okay, let me speed up because I'm running out of time. So before I said, and that's definitely something that can be proved, is that you are bounding it with respect to the order of H. And so if you want to be on the safe side and be able to claim that, that this error is indeed insignificant, you've got to know something about the H with respect to, there shouldn't be equality, with respect to the size of the same maximum F matching. And this is where this first phase comes to play. That's why we want to reduce H so that this new graph is really useful for application of this procedure. Well, let me mention that it turns out that you actually don't need this assumption of being Km minor 3, although that's something that I am assuming in this talk. A result of Amir, Schmidt, and Seibert from 2019 shows that you can come up, you can do this type of a clustering in graphs of bounded expansion, provided this expansion is small O of log R. Okay, so this really does extend to a wider class of graphs. Now, I am running out of time, so I will be really speeding up significantly right now. But let me say that this phase 1 is substantial. So this one is done ad hoc. Again, the objective of phase 1 is to reduce graph G to a graph H so that this graph H is useful. And it turns out that you indeed can do that. Okay, so you can come up with such an H. It's not difficult to come up with it in a distributed fashion. You can do it in a few rounds, and by a few I mean a constant number of rounds. But the analysis that it indeed works is actually quite non-trivial. Okay, so when you look at even planar graphs, there are obvious obstructions to having a maximum matching which is proportional to the order of the graph. Okay, that's one such obstruction. So two vertices that are adjacent, that are incident to many other vertices, or just one vertex, a star, just incident to many other vertices. Obviously, out of these, you can choose only one edge for a matching, but the number of vertices can be large. Turns out that these are, or generalization of these are, the only obstructions that you will encounter when analyzing this problem of reducing the graph to H. So what we deal with the notion of an I-clone, which is, so two vertices are called I-clones. They have the same neighborhood of size I, and we carefully eliminate them. Not going to go for this, but we do eliminate them. This, for the problem of F matchings, this must be done really carefully. We obtain this fact, we obtain some auxiliary fact, and from that, we can prove that indeed the size of maximum F matching in this reduced graph H will be proportional to the size, to the order of H. This relies on a structural theorem of Galay and Edmonds, and I'm not going to go through it. And yeah, the analysis critically depends on these previous lemmas and then the structure theorem of Galay and Edmonds. Rather than doing this, let me summarize the second part of the talk. So yeah, in the graphs which are Km minor 3, we can find an F matching F such that the size of it will be at least 1 minus epsilon the size of an optimum. And this can be done in log star n rounds. Of course, the constants here, they do depend both on m and on this epsilon, and they can be quite exponential. Okay, so it's not something that we really pay too much attention to. And the final sort of comment that I want to make, I am really done, is about these B matchings. So one might think, and we have applied this technique quite a lot, and one might think that this phase one of reduction can sort of be always done by appealing to same fix. But it is really not the case. So what you do for matchings will not necessarily extend to F matchings. And what you do to F matchings will not necessarily extend, especially as far as analysis is concerned, to B matchings. So in the case of B matchings, we can do something similar. But there's sort of a price that we have to pay. So it's not for all functions B, but in this theorem, we do have to assume that this function B satisfies some bounds on the locality condition, like say it's Lipschitz. Okay, so I guess with this comment, it's I'm really done, and thank you very much for your attention.
Thank you for a very nice talk. Any questions?
I have some questions. In the second part of your talk, you were talking about the F factor and the B matching in Km minor 3 graphs. I was wondering if you like relax the problem. Let's say we just want to find maximum matching. Is it possible to generalize this approach to like H minor 3 graph for any H? Like, for example, is the matching linear in the number of vertices? Can you do something to make the matching to be linear in the number of vertices if we only consider the traditional maximum matching problem? And yeah.
Yeah, thank you for the question. So I didn't have really time to speculate on this aspect. But when you look at this, let's just say, let me go back here. Where do I have this fact? I'm sorry, I can't find it. Oh, here it is. Here it is. So it turns out that in this reduction phase, you actually don't need that strong assumption that the graph will be Km minor 3. And so this will work for graphs of bounded arboricity. In fact, the only thing that seems to be needed is a bound for this nabla 1 of G. So basically, the bound for the degeneracy of a graph which is obtained by contracting. I mean, the only thing that we contract in the proof is edges. Mm-hmm. So that's enough to reduce. Now, I don't have time right now to really talk about it, but turns out that once you do this reduction, you can play with this reduced graph, and you can, I mean, it will still cost you more than just a constant number of rounds. You will have to apply Kolvishkin, so it will be log star of n number of rounds, but you will be able to find an approximation. You have to be careful here, but I do mean 1 minus epsilon approximation of a maximal F matching.
Okay. But what if you can't apply Kolvishkin here? Is there anything? Is it still possible to do something like that? I'm just
so yeah. So so if you want to beat log star, then I think that you will run into problems with Lineal's lower bound. I mean, Lineal's lower bound is for the maximal matching. Obviously, then it extends to maximal F matching because this will be a special case. But you will tell me, okay, you don't care about maximal, you want approximation. But I think that it still will be an abstraction. So I sort of don't believe anything will happen below log star of n number of rounds.
I see. Yeah, because in one of your work, you were doing this kind of clustering where you didn't apply Kolvishkin. You just decompose the graph into multiple components, and then each component compute approximation of the matching locally. There, I think you avoided Kolvishkin, I think.
Yeah, so I think that sort of in this clustering, the Kolvishkin is hidden in something that I skipped. And it will be not in phase 1, but in this phase 2. So in this theorem and in the previous theorem, you do need to find sort of a coloring of which uses a constant number of colors, and this is called Kolvishkin or something like that is being invoked. Yeah.
I see. Okay. Thank you.
Thank you.
And I have one question. I think the place that you use in the decomposition, you don't need the local model. Yes, you just conjugate model is enough. And but where you use locality, I think was to find I-clones. Yes.
Yeah, that's absolutely. Well, no, I don't think that maybe I-clones, because see, I will be constant as well. So I mean, it's definitely an obstruction in using phase 2. I don't want to make any definite claims, but I would say that phase 1, and I have to think about it carefully, but definitely in the analysis which uses this Galai-Edmonds, I don't think you need locality. I'm almost certain that even when reducing these I-clones, you do not need locality. You do not need the local model that much.
Then in the second phase, you also don't need the local. Yes, or I'm missing something.
I think that in the second phase, I do need local. I mean, at least that's how we came up with. I mean, when finding the optimals, we definitely rely on the fact that this is a local model.
All right. Oh, sorry.
Okay, so maybe we can say that it's officially the break.
Oh, right.
Then people can continue to discuss, obviously. But okay, if you want to leave to eat something or something, that's the moment.
Once again, thanks for a nice talk. And
yes, that's right. Thanks.
How long is the break?
Thank you very much.
Break right now. And
how long is the break? How long is it?